This is metrics everywhere. And today what I'm going to do is I'm going to talk to you about how to make better decisions by using numbers. My name's Coda. You've probably seen me on Twitter yelling about things that I don't like. Maybe on GitHub working on things that I do like. I'm the infrastructure architect at Yammer.com, which is the enterprise social network. And a big part of what I do at Yammer is I write code. But that's not actually my job. That's not actually why I take a paycheck. The reason why I take a paycheck is because I write code that then generates business value, right? And immediately this should raise the question in all of your minds, what the hell is business value? I thought this was going to be about numbers, and here I am standing in front of you spouting B-school bullshit. So it turns out that we as software engineers are actually intimately acquainted with business value. Because we're so involved in the creation of things, because we're so involved in construction and creating new things, we know what business value is, and we see it every day as we work. Business value means shipping a new feature that the users absolutely adore. It means going back to an old feature that never actually really worked and really making it pop this time. It means writing code with fewer bugs, which means fewer support tickets, which means less time spent in Jira or probably here Pivotal Tracker. It means not pissing our users off with a slow site or an ugly site or even a pretty site, right? Because it really depends on your users. It means refactoring your code and having well-factored code to make future changes easier. It means adding a unit test before you fix that bug, so you'll never actually have to fix it again. All of these little moments of win that we experience as software engineers, that's business value, right? Because business value is anything which makes people more likely to give us money. And because we like money, we want to generate more business value. And as software engineers, what this means is we need to make better decisions about our code. And we can't do this unless we realize a couple really important things. The first of which is that our code generates business value when it runs, not when we write it. People don't give us money to take the code and put it up on the wall like a trophy. People don't give us money to take the code and read it late at night in bed. They take the code, they run the code, they give us money for that because of the functionality our code provides when it runs, which means that in order to make better decisions about our code, we need to know what our code does when it runs. And we can't do this unless we actually measure that. Now you should be asking, why measure that? Why can't, I know what my code does, I wrote it. The reason why we need to measure it is because of kind of a basic fundamental truth about reality. And that's the map is not the territory. This is the famous dictum of the Polish philosopher Alfred Korzybski. He said a bunch of really crazy shit, but this one he's actually right about. Right? General semantics I'm not necessarily on board with. This, however, is true. In the same way that a map of San Francisco is not actually the city of San Francisco, as anyone who's tried to tell someone how to drive down Market Street knows. The way that we talk about something isn't actually the way that that thing is. Even the thing that we think of is not actually the thing in and of itself. It's trite, but our perception is not actually reality. And because both our understanding of what's going on and what's actually going on, both the map and the territory are in a constant state of flux. There's always a gap between what we know and what actually is. And we need to mind the gap. For software engineers, this matters a lot because we have a mental model of what our code does. This is what we use when we write our code, when we work with our code, when we track down that bug, when we predict the effects that a particular change will make. But it's a mental model. It's not actually the code itself. And our mental model is often wrong. And very much like someone attempting to drive down Market Street, when our mental model is wrong, we experience this as confusion, right? We say this code can't possibly work, right? But it works. You got to mind the gap. We say this code can't possibly fail, and then it proceeds to blow up. You got to mind the gap. But minding the gap in our profession especially is hard. There's no physical correlate for what we do. right? We don't have an off-kilter chair to remind us that we're a bad carpenter. We spend so much time inside of our heads, it's very easy to mistake the inside of our heads for reality, to mistake the map for the territory, right? For example, which of these two code samples is faster? Items.sort by I.name or items.sort A.name compared to B.name? And I know especially here that there's at least one person in the audience who's thinking, well, the first one's an example of a Schwartzian transform. So despite the fact that the complexity of the underlying sort algorithm is the same, the lambda in the first one is evaluated in times, whereas the lambda in the second one is evaluated in log n times, which means that despite the fact that the first one uses more space, it's actually faster in terms of runtime. Right? So which is it? Which one's actually faster? We don't know. We don't know which one is faster because we're working with our mental model. Right? And in this case, the first one got monkey patched to have a 100-second sleep in it. Right? So sort by is probably not faster here. Right? And unfortunately, sort is no better. It actually just blows up. Right? So it's not just that we don't know in this particular case, it's that we can't know until we measure it. And as software engineers, this affects how we make decisions. It affects how we spend our time. It affects how we allocate the resources that are given to us by our employer or by the sweat off our brow if we're self-employed. For example, right? Your boss, your manager comes in. She says, our application is slow. This page takes 500 milliseconds to run. That's unacceptable. Fix it. Right? And so you crack open that bit of code in an editor, and you look it over, and you play the game that we all hate to play, find the bottleneck. And so you look at the code, and you kind of think it over, and you think it could be an SQL query, right? We may need to hint an index. We may need to redo this. It could be template rendering because we just dried up a lot of the templates in a big refactor. We may have introduced a performance regression there. Or it could be session storage because I just read this really cool blog post about memcache and slab sizes. So which is it? Which of these do you work on? Which of these do you spend your time on? Which of these do you allocate resources towards? We don't know. And that's what makes that such a frustrating game. So let's play it again, and this time with a little twist. But I want you guys to pay attention to how you're thinking about this problem, right? So we're going to play Find the Bottleneck 2.0. And I'm just going to straight up tell you that the SQL query took 53 milliseconds. The template rendering took 1 millisecond. And session storage took 315 milliseconds, right? Where's the bottleneck? It's right there. Right? Did you see what happened when we added that information, when we added that extra layer of data on top of what we were doing? All of that confusion that we had vanished, right? And as a result, we made a better decision. We made a better decision because we improve our mental model by measuring what our code does. Map's not the territory, it'll never be the territory, but we can always have a more accurate map. We can always have a map which is more faithful to the territory. We can always improve our mental model, and that's critical because we use our mental model to decide what to do. And naturally, a better mental model makes us better at deciding what to do. Specifically, it makes us better at generating business value. So the gist of this is that measuring makes your decisions better. It removes that confusion, it removes that frustration, but only for measuring the right thing. And this is really important, because if I told you that the session rendering had taken 3 milliseconds instead of 300, you would have worked on the SQL query, right? You would have wasted your time. You would have wasted your resources. So it's critical that we need to be measuring, it's critically important that we're measuring the right thing here. We need to measure our code where it actually matters. We need to measure our code in the wild as it is actually generating this business value that we care about. Specifically, we need to measure our code in the magical land called production. Not on your laptop, not on a test cluster, not on EC2, unless you're actually running on EC2. We need to be continuously measuring our code in production. And at Yammer, we do this with a library I very originally called metrics. It's written in Java, has a Scala facade, integration points for a bunch of different things. It's MIT licensed, it's available on GitHub. And it gives us a toolkit of 5 different ways of measuring what our code is doing in production. gauges, counters, meters, histograms, and timers. So each one of these is associated with a class, which is where what it measures lives, and it has a name, because random numbers are really hard to figure out at 3 a.m. And so to kind of walk you guys through this and explain how you might use this in your application to improve your decisions, just go ahead and walk you through an example application. So let's say we're building an autocomplete service for city names, right? Real simple web service. You say complete Safra, and it says San Francisco. And so as we are gathering requirements, as we are writing tests and code, as we're putting together the staging environment, as we're putting together the production environment, as we're maintaining this over time, we need to be asking ourselves two questions. One of which is, what does this code do that affects its business value? And then, how can we measure that? Well, you can measure it with one of these, probably. If you can't, I would like to talk to you. So let's talk about what our theoretical autocompleter does that actually affects its business value, right? And how we can measure that. So let's start with gauges. A gauge is the instantaneous value of something at a particular point in time, right? So what is a value of this autocompleter that actually affects its business value? How about the number of cities? Because if your autocompleter can only complete 3 cities, then it's really only useful in like a post-apocalyptic scenario, right? One of them is Bartertown, and I'm not sure what the other two are. I haven't seen those movies, but and on the other kind of side of the spectrum, if you can complete 3 billion cities, then things are seriously interesting, but probably broken. So we can measure this with a gauge like this, and we give it a name, cities, and it has a callback associated with it, and we return the number of cities in our list or prefix tree or whatever we have. And with this gauge, we can say the service has 589 cities registered. That's what you get with a gauge. Next up are counters. These are pretty much exactly what you would expect. They're an incrementing and decrementing value, right? And so with for a web service, one of the things that you might care about is the number of open connections. You don't actually have those connections lined up in a big list, but you can count them. And so we can create a counter. We can give a name, connections, and when someone connects, we increment it. When someone disconnects, we decrement it. And if we have this counter, we can say there are 594 active sessions on that server. Pretty simple. Next up are meters, and this is where things actually really start to get fun. So a meter is the average rate of events over a period of time. And because our autocompleter is a web service, the kind of classic example of this is the number of requests per second that our autocompleter is doing at any given point in time. And you can measure that with a meter. Create one, give a name, requests, and you can give it a rate unit. So we're measuring requests per second. And then when a request happens, we mark the occurrence of that event with the meter. Usually when people talk about rates, usually when people talk about things per second, they're talking about the mean rate, which is the number of events divided by the elapsed time it took those events to occur in, right? So we say miles per hour, miles driven divided by the number of hours it took to drive that distance. And so we can take that and we can map that onto what our autocompleter is doing, right? So here are the number of requests being processed at each particular instant, which isn't actually a thing, but we'll assume it is, each instant of time, right? And you can see it goes up and down like a regular process. It's normally distributed, but that there's 2 inflection points right here and right here where the rate changes, right? It looks like it's being used more. And so if we graph the mean rate against this, it looks like this. You see there's an initial instability, and then it literally regresses to the mean. And then at the first inflection point, it kicks up slightly, and then the second inflection point, it picks up even less. And at the end, we're actually kind of presented with this weird gap between what we think is happening and what actually is happening. We know that we need to mind the gap. So the mean rate is not actually the process. And specifically when it comes to rates, we care very much about a sense of recency. We care about what the process is doing right now, not some kind of historical trivia. And the mean rate provides us with the rate over the entire period of the service's lifetime, which is not what we want. It's not useful. And so to actually come up with a rate which makes a lot more sense, which maps much more closely to what we care about, we turn to math. Specifically, we turn to exponentially weighted moving average, which These have been used in industrial processes for decades. It's been kicking around the guts of Unix for easily 40 years. And so it looks a little something like this. And you don't actually need to memorize that. But the one important thing is that there's a constant, alpha, which is the smoothing factor. An exponentially weighted moving average that has a high smoothing factor is very insensitive to variance in the underlying data. A low smoothing factor means that it's very sensitive to variance in the underlying data. And so if we go back to what our process is doing, we can chart a exponentially weighted moving average over this. This has a very low smoothing factor, so it's banging up and down a whole lot. You can see at the 2 inflection points that it actually changes to when what the process is doing changes. And so we can increase the smoothing factor more and more. And you can see that this red line here is actually like really a faithful metric of what our process is doing over time. And so the meters in metrics calculate a 1-minute rate, a 5-minute rate, and a 15-minute rate using literally the exact same formula that the Unix load average does. And so if we have a meter on our autocomplete service, we can say we went from 3,000 requests a second to less than 500 requests a second. You can see how recency really does matter. That's what you get with a meter. Next up are histograms. And these are by far my favorite. This is where things get really fun. A histogram measures the statistical distribution of values in a stream of data. Right? So what's a stream of data that this service is processing or generating that we care about the statistical distribution of its contents, right? Well, how about the number of cities returned? If our autocompleter returns mostly 0 results, not very useful. If it returns mostly 300 results, again, there's just not that many places named San something. So this matters very much as far as business value goes. It's something that we potentially deeply care about. So we can measure that with a histogram. We give a name, response sizes, and then when we have a response, we update the histogram with the number of cities in that particular response. And the histogram measures the statistical distribution of values in that, and it has the usual suspects like minimum, maximum, mean, and standard deviation. But the thing about these is that these are really good, the mean specifically, the mean is a really good measure of centrality for normally distributed data. For data which is not normally distributed, which is to say the vast majority of data that we as software engineers see, it is not useful at all. Right? How many times have you done something and you've got the mean and the standard deviation, and the standard deviation is several times larger than the mean, right? All that's telling you is that you've got 2 numbers which are useless. So what we really want, as kind of a general purpose tool, is we want quantiles. We want the median, we want the 75th percentile, we want the 95th percentile, 98th, 99th, and then, because I'm a bit of a perfectionist, the 99.9th percentile. But the way that people usually calculate these is they keep a giant sorted list of all the values. And then to get the 75th percentile, you go 75% of the way in, and the value there is the 75th percentile. Right? But we can't possibly keep all of these values, especially for high-performance services like we build at Yammer. If you have a service which is doing 1,000 requests a second, and each one of those requests, you're measuring 1,000 different things, and if you do that for a day, you're going to end up with about 86 billion values. And for 64-bit integers, that's about 640 gigs of data, right? Now, there's clever things you can do with, like delta compression and variable length encoding, but it's not going to happen. We need a better tool. And for that, we naturally turn to math. We use a technique called reservoir sampling, which is that we keep a statistically representative sample of the stream of data. And instead of attempting to perform the quantile measurement over the entire stream of data, instead we make that measurement on a small, around 1,000 element sample, and the results are statistically representative of the underlying data. It's a really cool technique, really not nearly as widely known as it should be. The canonical way of doing this, I'll take questions afterwards. I'm sorry. The canonical way of doing this is Vitter's algorithm R. There's a reference right there. I can't really get into it, but it's a pretty cool algorithm. And we can take a data set from our hypothetical service. So this is the number of cities that it's returning in each request over time. And because it's set up on a slide, there's 2 inflection points, about 2/3 of the way in, where we start returning more cities. right? We don't know why. Did the search stuff change? Whatever. This is the behavior of the process. And so using Vitter's algorithm R, using this algorithm for reservoir sampling, we can calculate the median, 75th percentile, and the 95th percentile. And you can see at the first inflection point, they don't actually change, and then at the second inflection point, they change even less. And by the time we get to the end, you can see just visually, there should be 95% of these data points underneath this line. It's a 95th percentile. That's what it does. That's more than 5%. That's a lot more than 5%, right? That there's actually this big gap, and by now you should know that we need to mind the gap. The reason why there's that gap is because Vitter's algorithm R produces uniform samples. These are samples which are statistically representative of the data that the service generates for its entire lifetime. But we care about recency. We care about what it's doing right now. So how do we calculate quantiles with this sense of recency? Well, we turn to even more math. And I realize that I'm hitting a lot of math, so here's a picture of my kittens. They're not this small anymore, and they like to play hockey at 4 a.m. But they're very cute when they're asleep. So, deep breath. So we do this with a technique called forward decay priority sampling. And there's a reference right there, kind of a 1-2 punch. Kittens math. Reference right there. The slides are online. I don't have enough time to talk about it really in depth, but it's an even cooler technique. But the gist of it is that this allows us to maintain a statistically representative sample of the last 5 minutes of data, or X minutes. We chose 5 because that's kind of the granularity that we care about. We don't have to store all of the data, but we end up with a statistically representative sample with an actual sense of recency to it. And so if we go back to our data set, if we're using forward decay priority sampling, we can calculate the median, 75th percentile, and 95th percentile. And you can just immediately see the change. At the first inflection point, all of a sudden this kicks up. Second inflection point, all of a sudden this kicks up. And by the end, like you can see, about 95% of those X's are underneath that red line. If you put them back to back, it's even more pronounced. Which one of these does a better job of measuring what the process is doing over time? Biased. And so if we have a histogram for the number of cities in our autocompleter service, we can say something like 95% of our autocomplete results return 3 cities or fewer. Is this good? Is this bad? We don't know. But we know that this is true. That's what you get with a histogram. The next up are timers. And timers are basically a compound metric. They're a histogram of durations and a meter of calls. Right? So we're already getting requests per second, but we don't just care about throughput, we also care about latency. We want to know the number of milliseconds that it takes us to respond. We want to know specifically the distribution of that data. And we can do that with a timer, like this. We give it a name, requests, because we're replacing the meter, and we give it a duration unit, or milliseconds. So we're measuring the time that each request takes in milliseconds. We give it the same rate unit, seconds, because we're measuring requests that happen per second. And then we pass the timer a callback. It measures how long that callback takes to execute, updates the histogram, and marks the occurrence of that event in the meter. And so if we have a timer on our service for this, we can say at around 2,000 requests a second, our 99% latency jumps from 13 milliseconds to 543 milliseconds. Hugely, hugely important from the perspective of someone who actually cares what their code does once it hits the server. So what you give it a timer. So we have these 5 tools: gauges, counters, meters, histograms, and timers. Cool. Now what? Now what do? Well, the first thing you do is you take this toolkit and you go through your code and you instrument it. And the rule of thumb that we have is that if it could affect the business value of your code, add a metric. If it could affect the business value, start measuring it, right? To give you a baseline for comparison, most of our services, which are very small, composed code bases, export about 40 to 50 metrics. Each one of those contains anywhere from 1 to 10 different measurements. So some of our larger, more complex services are actually exporting about 2,000 values about what they're doing at any particular time. Okay, so you go through and you instrument your code. Now what? Now you collect that data. If you're just measuring these things so that, when you're curious, you can come by and see how your pet rock is doing, that's not enough. You need to actually have an automated process for going around and collecting this. So the metrics library has a servlet which exposes the values of a service's metrics as a JSON object over HTTP, which is great because everyone speaks those two things. And so we have a set of scripts which come by every minute and collect this data from all of our services. Okay, so you've collected this data. You've got a big heap of data. Now what? Now you monitor it. And you can do this with Nagios or Zabbix or whatever you want. But the critical thing is that if it affects the business value, someone gets their ass woken up, right? So if your 99th percentile latency jumps up at 3 in the morning, you get a page. Or someone who can actively deal with that gets a page. Once you've got monitoring set up, you then start to aggregate this data. And you can do that with Ganglia or Graphite or Cacti or Muna, and there's a whole bunch of tools there. They're all horrible in slightly different ways, but they're there. And you don't have to build it yourself yet. And this allows you to place current values in historical context. This means that you can then see long-term patterns in the behavior of your code. And this is really where the rubber meets the road. Because if you get this process set up, it allows you to go faster. With this process, we can shorten our decision-making cycle. And this is critical. Our decision-making cycle looks a little something like this. We observe something about the world. We take that observation and we orient it within all of the other knowledge that we have, within our strategies and desires and tactics and fears, all the various things that kind of compose who we are as organizations. This allows us to extract meaning from the observations, which means that then we can decide what to do, and having made a decision, we can then act. This should be familiar. It's the OODA loop, which is a piece of military theory that Colonel John Boyd, who was a pilot in the Korean War, came up with. It applies to fighter pilots. It also applies to software engineers. There's less shooting and flames, but it's still the same process. We make an observation about the world. What is the 99% latency of our autocomplete service right now? It's around 500 milliseconds. Oh. We take this observation and we orient it within all of the other things that we know about software, about this software, about other software. How does this compare to other parts of our system, both currently and historically? Well, it's 500 milliseconds now. It was 50 milliseconds last night. I think something may have changed. It's way slower. Now we have meaning about this observation. Now we can decide what to do. Now we can decide where to allocate resources. Should we make it faster? Or should we add a new feature? Well, in this particular case, a 10x slowdown is probably bad, so we should probably have someone make it faster. Having made our decision, we can then act. And we get to write some code. Specifically, we should probably remove that sleep. And this is an iterative process. This is constantly happening. We observe the consequences of our actions and orient that with what we know about how we act to come up with, to make decisions about whether or not we change tactics or strategies. And then we can actually make those changes. So we have this cycle, we have this decision-making cycle. And if we iterate faster, we will win. A shorter decision-making cycle is a huge cultural advantage. It's a huge cognitive advantage. It's a huge competitive advantage. If your decision-making cycle is shorter, you will ship fewer bugs because your mistakes will not live as long. You will ship more features because you won't be working on things that don't matter. This means happier users. And happier users should mean more money. So I've covered a lot of ground here, and I kind of want to sum it all up. First, we might write code, and chances in this room, really high, we probably do write code. But we have to generate business value. And in order to know how well our code is generating business value, we need metrics about that code. We need to know what that code is doing in production. So Yammer, we've got this toolkit, provides gauges, counters, meters, histograms, and timers. instrument your code, know what your code is doing, monitor these values for current problems so that you can respond to those problems in real time. Aggregate these values for historical perspective so that you can see long-term patterns in what your code is doing in production. Because the map's not the territory, but you can always have a better map. We can always improve our mental model of our code because we have to mind the gap. And minding the gap means that our OODA cycle gets faster. Our decision-making cycle gets faster. And we win. So if you're on the JVM right now, you can use this library that we wrote. If you're using Java, Scala, JRuby, Jython, Clojure, Fortress, Mira, Phantom. Did I miss anything? There's a lot out there now. Groovy, sorry. So it's MIT licensed. It's available on GitHub. About the time it takes you to get a jar, you can start using it. If you're not on the JVM, you can build this. You can actually build this. If you're using Ruby, there's the Ruby metrics gem, which my friend John is working on. If you're using JavaScript, my coworker Mike Gidpy has a JavaScript library which does a lot of this. If you're on Erlang, Joe Williams from Boundary has Folsom, which has a lot of these same tools. If you're not on any of those platforms, though, you're capable of actually implementing all the stuff that I've talked about, all the algorithms, all the data structures, all the techniques, all these things completely and totally within your grasp. And it's not just, you can build this, but please, please, please build this. Because I think that you can benefit from having these tools, from knowing what your code is doing in production, always, as it's generating business value. I think that if you have this, you can make better decisions by using numbers. Thanks.
Can we say the Ruby and JavaScript names?
Sure, the Ruby gem is called Ruby Metrics.
Okay.
I don't know what the JavaScript library is called. It's on GitHub. My coworker is Mike Gidpy, IBHE.
Great.
You had a question earlier.
Yeah, as sort of like a general sort of strategy question. So your library is sort of fundamentally about having the pieces of software that are doing work be interested in the kinds of data you want about what they're doing. And you, right? I mean, they know, oh, I want a moving average of this. Oh, I want Instagram of that. Right? And there's sort of another like high-level strategy of, well, the software that's doing work should just have detailed event logging, send it all to somewhere, and then post-process, have a system that post-process that in the same.
That's totally possible, and for some things that's a very good strategy. I know there's StatD where you basically craft UDP events at kind of an aggregator service, and then it tells you statistics about that service. The reason why we have an in-process approach is because we're at Yammer we have a lot of services which are doing things where if we were to start crafting that data over UDP, we would have like two scaling problems, right? We would have the thing that we're trying to do, and then we have kind of the consequence of attempting to log massive amounts of data, and then either bang those over into an asynchronous process or a process that can then batch commit to that, or just kind of this death by kind of trickling little bits of data out of socket constantly. And so really what we wanted to do is we wanted to push that that aggregation up to the kind of the application level, so that we could keep the aggregation level relatively simple.
Thanks.
How did you feel about like using SQL technologies to actually track all this data and like have, like when someone makes a request to a server, a table and database gets updated, and then specialized SQL queries are used to like analyze data?
So that's all fine and good, but then you have to find a database technology which provides you with a relational model which can handle hundreds of thousands of writes a second. I mean, again, this is the same kind of like thing. Like if we already have one scaling problem, and introducing another one is not really something that we want to do. That said, I think that there's a tremendous amount of value provided by the relational model in an analytical role. Currently, we have an analytics group, which is really good. It's a bunch of economists and social gamers, so they're just like cutthroat bastards. But we have this excellent kind of analytical pipeline, so that we really do have a preposterous amount of insight into what our users are doing. And that uses Vertica, which is an analytical corner data store with some distribution stuff built in. I really want to use their data warehouse to analyze my numbers. But I think that at some point you have to choose your granularity because there's this massive thing, right? That if you're talking about the service which is deployed on 50 machines and the raw data is like many megabytes per second, and then you have to put that data somewhere. And so I'd much rather figure out what the actual point of aggregation is, and then collect and aggregate that, the rate as opposed to the existence of things.
You mentioned that some of your services have anywhere between 20, 100, or 1,000 data points that they're exporting. In terms of just writing your code and implementing it as you go, what kind of strategies have you developed for deciding as you write what's important to measure and what even could be possibly important to measure? And how does that avoid basically at one point does it get to be too much of a hassle to be implementing the entire thing manually?
So one of the reasons why we decided to go with manual instrumentation as opposed to kind of the more kind of like just profile everything all the time is because your profiling is very rarely at the granularity that you care about, right? Okay, this one method does this, but that's not actually really what you care about. What you care about is kind of this kind of larger aggregation of various different behaviors. So as far as kind of the balance between instrumenting and non-instrumenting, historically the way it's worked is we've written something and it does something unexpected and we have to bail ourselves out and we realize that we have this gigantic kind of like blind spot. And so we add instrumentation to it. And kind of, since we started using this approach, we've kind of developed a kind of intuitive kind of feel for, we're going to want to know about this. Like, this is going to come back to bite us in the ass. But it's still one of those things where it's like, we have a lot of metrics that we haven't actually looked at because it's, like you look at them and they're not a problem. But even that is still really useful because it means that this is something that you don't actually need to fuck with. Right, so we have this mental model of like, well, like what about your application is slow, and everyone's probably got this kind of cue of like, well, it's probably this or that, or this or this or this. But it turns out that that's actually tends to be an incredibly bad intuition of what's actually slow. Because there are things in our application where I was like, yeah, dude, this is totally going to be a problem. I can, so many optimizations. I can do this. I can store that. I can memorize this. I can blah blah blah. And it's like that takes about 2 microseconds tops. Like, move on. Like, this other thing takes orders of magnitude more time, has way more variance baked into it, et cetera, et cetera. So I think it's just kind of shaking things out.
Do you test your metrics collection in your code?
To some degree, yes. Not religiously. We are not a test-driven development shop. We test just in one way. We don't have hard requirements about testability. If it's something we can fuck up, we try to test it. And occasionally we surprise ourselves.
So, have you measured the cost of your measuring? And if not, how do you know you're providing a value?
We've done...
Jokes aside.
Yeah. Yoda.
Exactly. What percent of, what sort of overhead have you seen, and what do you think has been the win on, say, ballpark bugs collected, say, guardrail's not gone down?
Yeah, so the amount of overhead is trivial. So hooking up a timer to something, and a timer is kind of the biggest weight thing that we have, takes a small amount of memory. At any point in time, we have probably about 2 to 3 megs of heap, which is samples and such.
That's with your very heavy instrument, like 50 different things.
Yeah.
Totally, like using up.
Yeah, the amount of overhead that a timer adds is, after the JIT inlines everything, it's about a microsecond. So there's definitely some hot loops where you wouldn't want to do it. but there's been a lot of work put into making the metrics kind of aggregation and calculation as fast as possible.
This is done inside of the request, right?
Yeah.
What's the question?
Well, yes and no. So some things are done within the request, some things are not done within the request. Something like a meter, what it does is it basically increments an atomic variable in memory, which is real cheap, and then there's background threads to go in and decay that value.
How do you aggregate the aggregations? If you have like 50 web servers and they're all recording requests per second, you just have like one big page that shows like that stat for all 50, or do you aggregate those further?
Currently, I cry quietly while nipping a bottle of scotch staring at Ganglia. So this is one of the reasons why I really want to use our analytics team's tools, is because they have that shit baked in. Whereas Ganglia is just like, here, RRDs. Examine them for things. But some metrics are really easily combinable. For example, rates, you just stack those on top. And so we do have some dashboards for the stuff that we're doing. There's no general purpose tool which does what we do. There's one, aggregating quantiles is a little bit more different. More complicated in that you can't just kind of like average the two. And so what we have built in is the ability to export every histogram and timers sample, which would allow downstream aggregation to combine those. But at this point, our primary means of engagement with it are Ganglia and then monitoring. So if the 99th percentile of any of our services goes above 100 milliseconds, alarm bells go off, and everyone slides through the firewall.
Okay, so you have well-instrumented code. You have, aside from that being useful for monitoring performance in the wild production, it seems like it would be interesting to set up something like a CI server that is always running performance tests on code with whatever data set you want to use.
Yeah, so the cool thing about metrics is that it does double as a very sweet benchmarking library. So when we're curious about the amount of time that something takes up, metrics also has a console reporter, which every X seconds or what have you craps out all of the metrics to standard F.
So,
and so we do. So it would be totally possible to run performance regression stuff by saying, take this code, make sure it's exposing its metrics correctly, run it through a particular workload, and then send everybody an email if it gets slower than this. Basically, a kind of segregated system. Because if our stuff gets slow in production, they'll go off as well.
so do you have something like that? Do you have
No. No, in part because we find it very, very, very hard to simulate the sorts of kind of failure scenarios that we've seen in production anywhere else. That there's just something about unleashing a couple million people on something that really causes shit to come out of the woodwork, unlike anything else.
Can you talk, go maybe one level deeper on why you use reservoir sampling instead of just a random sample for getting a representative sample Instagram?
Sure. So that's effectively what priority sampling is. It's just basically how do you keep that random sample recent. So if the other drawback of a random sample is that it doesn't actually decay. If things stop, it stays at exactly the same value. It doesn't change. So if things slow down dramatically, the number of elements that you are adding into the sample skew the results less.
And that's how. I guess I just don't know enough about reservoir sampling, but how is that not true with reservoir sampling? It seems like you would have less.
With reservoir sampling, the probability, specifically with forward decay priority sampling, the probability that that particular element will replace any other element in the sample is an exponential function of time from a landmark value. And so basically, it gets more and more and more likely relative to old values that new values will replace it. So if all of a sudden there's this weird 5-minute gap where the kind of Nixonian 17-minute blank silence where everyone's staring into space awkwardly, that next value that's well, this thing took 17 minutes to complete, that is definitely going to the sample.
So for the CI injection tie, so it'd be kind of like retroactive and you just tie the rep to the I guess to all of the stats and we just have the CI server.
Yeah. I mean, we have not at all looked into the CI thing, in part because, I mean, I'd love to have another production cluster and then a gigantic set of load drivers to actually simulate the failure scenarios that we've seen in production. But for our stuff, with the high value elements have not been, well, this thing's slightly slower, this thing's kind of unacceptably slow. It's like, oh shit, you throw hundreds of thousands of users at this, and all of a sudden the HTTP client, Apache HTTP client 3.1, because of its desire to share mutable data between all threads, locks entire Dolphin's asshole. Like that's the sort of thing that you see in production that's actually going to cost us time and money.
Do you record sort of, what do you record about like, the state of your production? Why did that happen?
Everything. All of these values that we are calculating get collected by the scripts. Ones that are high priority get sent to Zabbix for monitoring. Everything else goes to Ganglia. And so we have these like acre-long like Ganglia pages that just have all the things monitored. All right. I think I've exhausted you. Thanks for having me, and thanks, Josh.